Hello everyone, this video will provide you with a general overview of multiprocessor with MESI cache coherence. So we have a big question, that is, what is MESI or MESI? The MESI cache protocol ensures cache coherence by assigning each cache line one of four states, allowing processors to coordinate access to shared data and minimize memory access conflicts. So, depending on the states modified, exclusive, shared, or invalid, we can accelerate the processors by minimizing the memory access, which is really important. This method will transition between the each cache block and the bus that connects each cache to the memory. So it's a bidirectional communication between caches and the bus.
This slide illustrates the multiprocessor system abstraction, focusing on four main components: processor, cache, bus, and shared memory. The diagram shows an MP system with four processing elements. Each processor is connected to its private L1 cache, which helps reduce memory access latency and improve performance by storing frequently used data locally. The caches are linked through a bus interconnect, which facilitates communication and ensures coherence between processors. This is crucial for maintaining consistency when multiple processors read and write shared data. Finally, the shared memory represents the global memory accessible by all processors. It provides a centralized resource for storing and sharing data between the processor, while the bus ensures synchronized access to avoid conflicts and maintain systems integrity. The system demonstrates the importance of cache coherence protocols and efficient bus arbitration to prevent issues like stale data or race conditions in parallel execution.
False sharing is a problem that can happen when computers with multiple processors, think of them as several brains working at the same time, try to handle tasks. Let me explain it in simple terms. Each processor has a small, fast memory called cache or cache that helps it access information quickly. The issue arises when two processors are working on separate tasks but unknowingly use a shared piece of memory called a cache line. Even though they're working on different things, if one processor updates something in that shred memory block, the other processor has to stop, refresh its memory, and then restart. This back and forth causes delays and slows everything down, kind of like two people trying to write on the same piece of paper at the same time. In the diagram, you can see that Core 0 and Core 1, two processors, are sharing the same memory block. Every time one makes a change, the other has to pause and resync, which wastes valuable time. The solution is simple. We can reorganize or separate the memory each processor uses so that they don't share the same block. This way, each brain can work independently and much more efficiently. In short, false sharing may seem like a small issue, but addressing it can make computers run faster and perform much better overall.
To further explain this, we can show an example using the simulator created by our team. In this case, we only have two processors working at the same time. P1 executes an store instruction to write a value into memory, which updates cache line 1 in its respective cache. Eventually, P2 executes a load instruction, which also involves cache line 1. Even though PE1 and PE2 are working separate data, you can see that both caches have the same line as shared. This shared cache line causes unnecessary invalidations and data transfers between caches, illustrating false sharing in action. Our simulation demonstrated that the MESI protocol is effective in reducing unnecessary memory accesses and ensuring data consistency across multiple processing elements. However, fault sharing posed a significant challenge that MESI alone couldn't completely address without architectural changes. Techniques such as adding extra space and aligning data more carefully were crucial in minimizing these effects. This analysis highlights that while coherence protocols like MESI are essential for shared memory systems, their efficiency can be heavily impacted by software level issues like fault sharing. To achieve the best performance, a combination of hardware solutions like MESI and software optimization techniques is necessary.